Yeah. And he's going to speak about uniform random expressions
Okay.
and how they do not have a lot of expressivity.
Yes.
Yeah. Okay.
Okay.
Welcome.
Thank you for the invitation. So I will present some work I did during my PhD with one of my supervisors, Cyril Nico, and another researcher called Pablo Ronquillo. So I will talk about uniform random expression, and the aim of my talk is just to convince you that they are lack expressivity. So when I'm talking about expressions, I want to deal with a lot of different expressions that you might kind of know. For instance, you have arithmetic expressions. So I just give you one example, something like 1 plus x times x. I want to be able to handle this kind of expressions. But there are other expressions that arise in other fields of computer science or mathematics, something like, for instance, Boolean expressions. So here I give another example. So x, so this symbol means or, not y. This symbol means negation. And I want also to be able to handle other expressions like regular expressions. So for this one, maybe you don't know what it is, so I will explain it a little bit later what they mean. Okay. For instance, a regular expression is this one. So I want to be able to talk about expressions, something that comes from mathematics, some other comes from computer science. And most of these expressions, they have some common things. They speak about different things, but they can all be represented as trees. Here, for instance, I can write a tree describing this expression, like this. This one, I can describe it as this tree. And this one, so you have the concatenation, which is binary, can be written as this tree. So to me, an expression is basically just one rooted label tree. So when you look at Wikipedia and ask what is an expression, it tells you that basically just a combination of symbols that respect some syntactic rules. So it's right, it's a label tree, but you cannot authorize everything. I mean, here times is called an operator. It's binary, so it has to have two sums, right? So it's just a label trees, and you have some symbols that you call constants that you will put on the leaves, and you have some internal symbols called operators, and they have a fixed arity. Here plus is binary. Here the negation is unary. All right.
But it may depend on the drawing of the tree if your operations are not like commutative, right?
What do you mean?
So if
okay.
plus would not be commutative,
Okay.
then
So in this talk I will not really talk about it,
okay.
to simplify, but yes, we can handle it. Okay, we can also handle sometimes some operators that would have different arities. So usually in this framework, I will only say that types is binary, but I could just have a one time that would be binary, one time that would be tertiary, and one for each arity. I can just label them if I want by their arity.
But I think he means if you switch that tree this way.
So the tree, the drawing of the tree contains the information about the order of the inputs, right? But not the tree.
If that arithmetic expression was matrices,
yeah,
that is not the same as multiplying x on the left.
Yeah, yes, exactly.
And that
yes.
you should
yes.
code
So
in
in
tree.
my case, yes, they are plain rooted. So okay, they rooted trees, but in the plane. You say. So to me, this is not equal to this. There are two different trees.
Right.
Yeah. Okay.
Sorry, what is the rule of reading the tree? I just don't understand. If I draw some tree,
Yeah.
how can I read an expression out of the tree?
It's more like I'm not sure to understand the question.
So
What
from
do you mean?
tree,
Start with the root.
I mean, an expression, it's something that is built upon some constant things that you will put on the leaves, and you have some operators that have a narrative. So,
So you have labels.
yes.
You have labels in the note, telling you what operations.
So it's a drawn tree with labels on each vertex.
And I guess order, right?
So
Also,
everything
like,
it's actually a drawing in the plane of a tree with labels on each vertex.
I got, but these two trees are the different. That's what he said. This means that
Yes.
the leaves are also ordered somehow. It's just more than the rooted tree. It's something
Yes,
more.
it's
Oh,
in
yeah,
the
yeah.
plane. The order, yes.
plain tree, yes, you have all the
Plain rooted tree. That's what he said.
So those trees are the same in the plane, I guess, is maybe the problem. But if you just have a path at length 2, it's only got one embedding there.
That's
They're not the same label tree.
yeah. So,
You
so
distinguish left and right.
yeah.
They're not the
You
same
have a left
plane
turn
label
and a
tree.
right turn.
You have a top, you've got a bottom.
It
you've
depends
got
on
left,
what you
you've got
mean by
right.
the same plane.
Yeah, it depends what.
Yeah.
what-
I think you just have ordering of the lead children, and that's enough.
Sorry, last question. Can you give us some other example, like to please draw some tree, which will be like 5, 6 vertices, and show me how I would read them. Please.
Okay.
I don't get it.
I will put a minus here, like this. So this means would be the expression represented by minus x times y.
Yeah.
So the way to encode the shape of your tree is to use parentheses when you're writing in on a string. But the idea is that you can get rid of the parentheses just by looking at the trees it is represented by. Is it okay?
Okay.
Okay. No problem. Okay. So expressions are represented by trees. And okay, so Wikipedia says that it's just a combination of symbols according to some rules, so just some label trees satisfying some syntax constraints. But why do we use them so much? It's not because we like to play with trees. We use them because they represent some mathematical object. Here on arithmetic expressions, it represents a function of x. Here, a Boolean expression, it represents some Boolean functions that were associated to the value of x and y, a truth value. And here, regular expressions, it represents a language. So, I just give you a very quick overview of what a regular language is, because I will need it a little bit later, and because most of this work has been motivated by the study of regular expressions. So regular expressions, there are expressions that represent some language. So a word on A and B is just simply a finite sequence of letters. So A is a word, AB is a word, BB is a word, etc. A language, it is a set of words. It can be an infinite set of words, but just a set of words of this form. And a regular expression is just a way to describe some languages. Okay, so A and B, they are considered as regular expressions, and they just represent the language that only contains the word A and the word B. Okay, and I also have a special word written epsilon that represents the empty word. It's a word that has no letter in it. Okay. So when I have an expression E and an expression E prime, I can build the regular expressions of the sum of the two of them, and the language represented by this, so which I write this like this, the language represented by E plus E prime is the union of the languages. So basically, A plus B, it represents the language AB. So this is a set of words. You also have another operation, which is a concatenation, that is I will not write it like this, but basically it's the set of all words that you can obtain by gluing one word of E with one word of E prime.
So the empty word is in every language?
No.
Oh.
For instance, it's not in the language A.
Ah, okay, okay.
No, it's not the empty set. It's really a special word that is empty.
Okay.
So for instance, A plus B times B, it represents the language AB and BB. You take a word in A plus B, so either A and B, and you glue B to it. And then finally, so this is called union, this is called concatenation. And finally, you have another operation which is called the clean star, which represents the set of all words that you can obtain by gluing an arbitrary amount of words in E.
Does that include 0?
Yes.
Yes. So A star, it represents the language epsilon, A, etc. Okay? So one language I want you just to remember, regular language, is the language A plus B star. So it's a set of words that you can obtain by gluing either an arbitrary number of letters in A and B. So it's a set of all words that you can do with the letters A and B. Okay, so just remember this. A plus B star is the set of every word you can do with A and B. Okay.
So just so I understand, so that there is all letters, all words made of A's and B's, but it starts with A?
Yeah, exactly. It's a set of all words that start with an A. Right. So the motivation to look at expressions is that as they represent some useful mathematical or computer science object, they are the entry of many algorithms that deal with them. So typically, if you are using DREB to do some pattern matching, you will have an algorithm that will take into as an input your regular expressions that represent the language, and it will look at your files, for instance, that has a name that satisfies this pattern. So it is the input of an algorithm, and then the algorithm will treat your tree in order to produce some result or some data structure that will be more suitable to analyze what the object represented by the expression. So, expressions, they are the input of many algorithms, and when you have two algorithms that kind of do the same thing, and they take as input expressions, sometimes you want to know which one is faster than the other one. So you have several methods to compare the efficiency of two algorithms. One is called the worst case complexity, which is a theoretical measure that says to you which one. So that says in the worst case, what is the worst complexity of an algorithm. So this is a measure of the time your algorithm will take, but on its worst possible entry. And so this complexity is a theoretical complexity, and sometimes it's not really relevant because the worst case input may not happen in real life. So when we want to be a little more realistic and look at real life, whatever that means, entry, we turn to random expressions in the hope that they may catch a little more what real life expressions look like. Okay? And we do this in at most two cases. When we compare two algorithms, we can just give them randomly generated expressions and just record the time they do to treat them. In this case, we are doing what is called benchmark. So it's more an experimental way of measuring the efficiency of some algorithms. And you have another more theoretical application of random expressions, which is called the average case complexity. So instead of looking at the worst case, you are looking at the average case. Okay, I really have a bad writing, so sorry. Okay. But when I say random here, random can mean a lot of things. So I have to say what is the probabilistic distribution of my expressions. So usually you want to have some probabilistic distribution that looks like the real life distribution of your of the inputs that your algorithms will have. But most of the time you don't have really any clue of what it looks like, and or sometimes it's not tractable mathematically speaking. So you have two usual distributions that are used. One is the uniform, and another one is called the BST for binary search tree distribution. In this talk, I will mainly talk about uniform one. Okay. So the uniform one is just you create an expression and you give the same probability to every expression that have the same number of nodes. So
you're counting internal nodes as the same as leaves?
yes, all nodes. So to me the leaves are also nodes.
So what about the number of nodes? Do you have a distribution of the number of nodes as well? So if you fix the number of nodes, you can talk about the uniform distribution, but number of nodes can be infinite, right? I mean, the trees can be unbounded.
Ah, yeah, I'm looking at finite trees, finite
And you
expressions.
fix the number n and then say consider
Yes,
distribution.
yes, exactly. I fix the size of my input. I want to compare my algorithm on n tree of inputs of same size, a fixed n, and I randomly choose expression of size n. So uniformly for this. Okay. So this looks like a nice idea, but when you look at the algorithms that are denoting benchmark, or at the output that that study the average complexity of algorithms, usually, most of them, I mean, almost every time, the way they generate these trees is completely syntactic. So they explain how to draw an expression as a label tree, but they never take into account the fact that these trees mean something, that they have a semantics. And this can be a problem because two different expressions as trees can represent the same object. So just one very simple example, x plus minus x represents the same object as 0. Okay. And you are, this happens in arithmetic expression, but also in Boolean expression and also in regular expression. So this phenomenon of redundancies happens a lot in a lot of cases of expressions. So if I look at my expression of size n, my set of expression of size n, and I looked at my mathematical object represented by them, so this is a smaller set. Here I'm looking at the what I would call the semantics of the expression. I can have an object here that is represented by several different expressions. And something, yeah.
But in this case, the two expressions that you have don't have the same size, right? Like on one side you have x plus minus x.
Okay,
That's-
okay. Okay, yes, yes. But I mean, this is not a problem. I mean, this is a problem for uniform, but this is not a problem that you may have several expressions not of the same size. I mean, this is also a big issue. And, okay, but what may endanger the relevance of benchmarks and average complexity using the uniform distribution is that you may have some object here that has a huge proportion of representative. And what I want to show you in this talk is that it happens a lot of time. In many cases, this will happen. You will have a constant proportion as n tends to infinity of expressions that will represent exactly the same object. So basically, when you are doing some benchmarks for the uniform one, you are testing your algorithm on expressions that most of constant fraction of the time on expressions that are representing the same object. And these expressions, they represent the same object, but they also are sub-expressions of other expressions. So they occur a lot, not as a full expression, but also as sub-expressions. So you can have some phenomenon of a huge simplifications of expressions. And this also may endanger the average complexity. Yes?
I have a question. Maybe you already said this, if so, sorry. For the uniform distribution, do you also assume your alphabet to be finite?
Yes.
There's like some fixed size.
Yes, yes.
So you don't use like the all integers or something?
No. I mean, I think it would be the same, but we didn't study it this way. But we can simulate them but it will increase the size just by having the constant 1 and plus. So,
that's true. Yes.
But in this case, it's not the same notion of size, right? If you have if you authorize any integer, you can say 1 million. It will cost only 1 in size.
Yes.
But if I have to encode it with 1, it will be a huge tree. Yeah. Okay. Okay, so I want to show that this picture occurs a lot. But I want to show it in a lot of cases. So you have, in the literature, you have some works that has been done specifically for Boolean expressions, for instance, or some others that has been done specifically for arithmetic expressions. But I don't want to do this because if I only focus on one class of expressions, maybe the result I will have will become too specific about it and we cannot be generalized. So my goal is to show that this happens, but using as little as semantics rules as possible. My goal is really to look at the expressions as label-rooted trees and just have one semantic rule, as little as possible, that is present in a lot of cases. And that suffices for me to say that this bad behavior happens. And this small semantic rule that happens a lot and that will be sufficient to prove this problem, this result, is the presence of an absorbing pattern. Okay. So an absorbing pattern, what it is? So P is called absorbing for an operator star if in the semantics of the expression you're looking at, every time you have P and just under this operator, the whole tree here is equivalent to P. So just let me give you some examples. For arithmetic expression, 0 is absorbing for times. Every time I have 0 under times, never mind what I have here, the whole thing is equivalent to 0. For Boolean expressions, this means true. It is absorbing for or. True or anything is always equivalent to true. And equivalently, false is absorbing for n. And for regular expressions, that's why I told you about this one on 2 letters, a plus b star to represent every word. So when I'm looking at the union of an expression and a plus b star, so an expression on the letter a and b, I'm looking at the union on everything and some subset of everything, so it's equivalent to everything. So this is the common point of the expressions I showed you. They admit an absorbing pattern.
Is that the right form? Oh, it's, okay, I got it.
Okay. So the framework I'm working in is just syntactic trees. So described by what is called a combinatorial system, and I will just give you example just after. Okay, combinatorial system, and only one semantic rule, absorbing pattern. P for an operator star. Okay. So my trees here, my expression trees, I look at expression trees that are defined by a combinatorial system. So combinatorial system is just a recursive way of describing your expressions. So I give you an example for the for arithmetic expressions. The set of arithmetic expressions. So inductively, 0 is an arithmetic expression, 1 is an arithmetic expression, and x is an arithmetic expression. And then so here I define the constants. Then I want to explain how I build some arithmetic expressions using the operators. Okay. So I have plus. So if I'm looking at two arithmetic expressions, the plus of these two arithmetic expressions is also an arithmetic expression. So this is what I write it like this. The times of two arithmetic expressions, so the product is also an arithmetic expression. And if I take minus, it's just to have a unary operator. The minus of an arithmetic expression is also an arithmetic expression. So this is what is called a combinatorial description. So when you write it exactly as a combinatorial system, you put an equal here, and you put some plus in between the construction I have there. Okay? And regular languages, it's the same. You have A, B, epsilon for the constants. Then you have the union. You have the product. And you have the star. Okay. So basically they kind of look like the same, right? Just the labels are changing, but they are built kind of the same. So actually, usually, my running example is this one with regular expressions, but as you may not be completely confident with them, I will mostly use this as a running example. So that's why I put a minus here, just to have the same shape and not have to redo the same some other calculus. I can redo the same calculus, right?
So for arithmetic expressions, you're only allowed to have one variable x and not multiple ones?
I could. I just give you arithmetical expression built on 0, 1, and x.
Okay.
But if I wanted to have more, I could have added some exponential, for instance, and another variable y. It means my framework is just any expression that can be described with a combinatorial system. Here is just one example. Okay.
But at least in your running example, we only allowed one x. Okay.
Yes, in this running example, it's only one. Yes. Okay. So one nice thing about combinatorial system is that they are really nice to use with what generating series and analytic combinatorics. Okay. Oh no, I forgot something. Sorry. I also allow some systems. So this is just one equality here. But for instance, imagine that I told you about redundancy. And you may say, okay, but here, look like, here you authorize minus something, anything. So basically, you allow your construction to build trees that are just like this, minus, 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 x. So you complain about redundancy, but you do not do anything to prevent redundancy here. So I want also to allow some systems, because systems they are nice to try to prevent some redundancy. For instance, if I want to have two minus on top of the other, I can describe it as a system of two classes. The first one will be the arithmetical ones. So here, I say that an arithmetical expression is either an arithmetic expression that do not begin with a minus, that doesn't begin with a minus, or it is a minus, something that does not begin with a minus. And then I just have to write what is an expression that does not begin with a minus, so it's just 0 plus 1 plus 8. I just put this, but I remove this term. Okay.
But that's then not the same, right?
This is not exactly the same, because here I authorize to have minus minus something here.
Right, but I mean, you can have like multiple minuses which in your expression which don't reduce to each other semantically, but so
Yeah.
so these types of expression are only contained to have one minus at the very beginning, right? What you're like-
No. Here I can have something that does not contain a minus at the beginning.
Right, but at most one minus, and if it contains a minus, it has to be at the beginning.
No.
No?
The recursive call.
It's
of-
recursive.
Yeah.
That's the point.
Here, for instance, I can start with this. Says, okay, so if I want to build a tree from this class, I can just build a tree from this class.
Okay.
Begin with this. And this one, you can start with something that is not a minus. But then I have put it A here. So I have to put some trees that belong to the class A. And it can contain a minus. Okay?
So it's
I see, so this is like,
Yeah,
there's
there
a
are-
weird self-reference thing.
Yes,
Yeah,
yes.
yeah.
There are
I
tra-
see.
yes.
Okay.
A is defined with A minus cross, and A minus cross depends on A. So they
Okay.
each one depends on the other. Yes.
So you can see how many recursions there is each thing.
Okay.
Yes.
So what is nice with this combinatorial description is that they work fine with generating series. So when I'm looking at my class of expressions, so represented by a combinatorial expression, a combinatorial description, I want to look at the generating series of my class. For instance, for the arithmetical, it's this one, which is the formal series that counts the number of trees or expression of size n. Okay? So this is also A of z. What is magical is that A of z, the combinatorial description automatically translates into an equation for A of z. So here, A of z equals, so every time I have a node, it is counted by z. So every time I have a node, I put a z. When I have a plus, I put a plus. That's why we write plus. And this can be understood as a Cartesian product. Instead of a tree, it can be seen as a Cartesian product. So this will be accounted by the product of the generating series. So here, A of z is equal to 3z plus 2z A of z square. So these are those two terms. Plus z A of z. Okay. And the whole principle, well, no, I mean one big idea of analytic combinatorics is to study this formal generating series as a complex function. Okay. So the idea is to look at the asymptotic behavior of this generating series around what is called its dominant singularity. And you can translate this as an asymptotic behavior of AN. So let me solve you this problem. So this one is easy because it's a 2-degree equation. So I can solve it. So I solve it for you. It's just this. Can be done and written under this form. When rho is minus 1 plus 2 square root of 6 over 23. Okay. And rho 1 is bigger than rho. So the idea of combinatorial of analytic combinatorics is that, okay, I forgot something here.
So what did you write over there? G row 1? Row 1?
Yeah. You have two. Okay. You have two roots here. Row and row 1.
Row 1?
Yes, it's another one. I mean.
Okay.
Okay, row tilde if you prefer. Okay.
What is row tilde?
I guess it's a plus minus maybe.
It's another one. Okay.
Complex country? No, not complex country. It's something.
It's another one. It's just
Alright.
bigger in the.
Yeah.
Okay. So the idea is here, this interpreted as a complex function, an analytic function. It has a dominant singularity as z equals to rho, equals to this one. So we say that around its singularity, its asymptotic behavior looks like this. So we don't really care about the constants, so I write them anyway, but it's not that important. But what is important here is that it looks like a square root function around z equals to rho. Okay? Yeah?
I'm sorry, I guess I missed a step when you define A of Z. So I guess what confused me, A of Z, like the second line on this, I guess I missed why you multiply each item by Z.
Yeah, okay. Each of these items, this or because you have some nodes here that count on the size of your trees. So it's just that. If I need to look at the size of these trees, then the left child counts in the size of the tree, the right also. So this is my A of Z square here. But I also have this one, this node, and this node counts at a Z.
So size is
Because it increases size by 1. So
so
that's
size is
Yeah.
number of all nodes in the tree, not just the leaves. That's why it's in.
The idea is that it's a Cartesian product of plus, which is one node counted by Z, and two child A of Z, and you just multiply the generating space. Okay. And when you have this, you have what is called the theorem, the transfer theorem. So. That says, under some nice analytic conditions, if f of z around its main singularity, dominant singularity, look like something like this, 1 minus z over rho minus alpha as the exponent, then, so f is equal to this series. Then the asymptotic behavior of the function translated to the asymptotic behavior of the Taylor coefficient. So an is asymptotically equivalent to 1 over, so this is the Euler function. So you have an exponential term coming from the singularity, and then you have an exponent for the n, but not polynomial, but of this form. So when you have minus alpha here, you've got alpha minus 1. So when I apply this to my problem here, I will get that an is of the forms a constant rho minus n here, and n to the power of 3/2. Okay? So here I treated one special example, my running example, by hand, and I use the transfer theorem to obtain this asymptotic behavior for the number of expressions of size n. But in fact, this is not specific to this kind of expression. There is one phenomenon that is called universality of square root singularity that says that for a lot of expressions described by this syntactic combinatorial system, they will behave the same way. It means their behavior will be described by this kind of asymptotic behavior. So, of course, the row here will change, but you will always have this square root singularity. Not always, but in a lot of cases, you will have this square root singularity. Okay. And this is called the Darmota-Lally-Wood with an S, theorem. So under nice conditions, all of my expression trees I will look at here, defined by some combinatorial system, not always just one-dimensional, they are counted by something that looks like this, with -3/2 here. Okay, so this is kind of a universal property of the expression I'm looking at.
Can you give some indication of how, what a combinatorial system that doesn't satisfy the hypothesis of this theorem would look like? Or?
Okay, so there is some condition in the Darmota-Lally-Wood theorem. So there are two types of conditions. One is because Darmota-Lally-Wood theorem is stated for a system of generating series. So you have several conditions that say that it really defines some, it has some solutions and things like that. But here we don't really care because our system comes from real life expressions. So this is kind of automatically checked. Okay. And there is one stronger condition, is that the system here, the system of dependence is strongly connected. So this system of dependence is exactly what we talked about just for your question here. Is you draw an edge from two combinatorial systems when the equation defining it depends on
so if you had like an A and a B and there was no way to get from
exactly in this
B
case
to A,
in this case you don't
then
you don't you don't have the hypothesis of the Darmota-Lally-Wood theorem.
Right.
So this is kind of a strong hypothesis, but in many cases in fact this is satisfied. So we looked at several ways, several articles that try to avoid some redundancy in some for regular expressions, for instance, and almost all of them satisfy this theorem. And even the ones that did not, they could be a little bit changed without changing the asymptotic behavior and made to satisfy the condition. So that's why it's called universality. Usually you have to do it on purpose not to have this. Okay? Okay, so now we are already ready, just checking here the time, okay, to prove this picture. Oh, almost. Okay, I forgot just one thing.
You have a more space there.
Okay. So here I've kind of I have sorted out the syntactic question. My trees are represented by some combinatorial system, and I have a framework, the Darmota-Lally-Wood theorem, that tells me that they are all counted kind of the same way. So now I want just to introduce my semantic rules. Okay, I have an absorbing pattern. So I define a reduction sigma that transform an expression into another one by using the absorbing pattern and reducing it. So basically, every time I can see a P under its absorbing element, I replace the whole subtree by P. And I continue up from the bottom to the up until I don't have any more P under its absorbing pattern. So if I take this example here, anything here. Here I have a 0 under times, so I will replace all this subtree by 0. But then I still have a 0 under times, so I will replace all of this thing by 0. And I get 0 plus 0. So as I said, it's a really not stupid, but very elementary semantic rule, so I don't know that 0 plus 0 is equal to 0. I'm just focusing on the fact that 0 is absorbing for time. Okay. And then I define the class R, so not the regular one, but the class of entirely reducible trees. For a class of expression, it's the class of all trees such that sigma of t is equal to p. So that's the class that will be completely reduced to the absorbing pattern p when I apply to them sigma. And this is my potential choice here of a big set here. So what we are going to prove is that if here I take the object represented by p, so maybe I mean I won't be able to capture all of the expressions that are exactly equivalent to p, but I will prove that the set of irreducible trees is already large enough. So this means that the pre-image is bigger, so it's already a problem. Okay. So this set R, I will prove this result for arithmetic expressions. Okay.
So for arithmetic expressions, p is like 0 and 0.
Yeah, p is 0.
Yeah, in this case, it's a set of formulas which gives you 0 automatically.
Yeah.
Okay.
Yes. So how do I build? Oh, okay, so I introduce R of z. It's just the generating series counting the number of elements of size n in R. Okay. And now to be able to compute R of z, I want to have a combinatorial specification of the entirely reducible trees. So what does a entirely reducible tree looks like? So first of all, I have 0. 0, it reduces to 0, so it's a entirely reducible tree. Okay? And now, if I'm completely reducible, it means that I have as a root a times. Okay? Sure. And basically, I'm completely reducible if in my root I have a times, and in one of my children I have an already completely reducible tree. It may be 0, but it may be some other guy in this class. So here I put the case when the reducible tree, at least the left child is entirely reducible. And here I put the case where it's the right child, but in order to count only once, in one time when it's the left one that is reducible, I need to avoid, in this case, the fact that the left child is entirely reducible. In the case I would count them twice. So here I put all arithmetical expressions that are not entirely reducible. Okay? So this I can completely translate into R of z equals z plus z R of z A of z plus z A of z minus R of z times R of z. And then I could just, I don't know what it is, but replace A of z by its value and then compute things and use the transfer theorem and prove it. But I want to explain to you a little bit of how I do this more specifically when I don't know the result of A of z, to give you a hint of how it can be generalized to any expression tree. So instead of just doing this,
why you do not consider R plus R? Is it already contained in that case, or is it
yeah, here R is included into A, so it's in this case. Yes.
Okay.
Okay. So for this case, so what I want to apply Darmstadt-Hollywood's theorem. The problem is with Darmstadt-Hollywood's theorem is that it does not like, I didn't tell you about all the hypotheses, but it doesn't like minus expressions here. Basically it wants to have everything is a plus here. So this set here, A minus R, it's a problem for me to apply directly the Untitled Theorem. So I will just introduce the class G, which is just the complement of the class R. So it's a set of expressions that are not completely reducible. So here I still have R that is specified by this. So here I put G, sorry. And then I can specify the class of expressions that are not completely reducible. So the beginning is easy. I know that these one are not completely reducible. Minus A here. And when I have a time here, I have to prevent that one of the side is completely reducible. So I have to put an expression that is not completely reducible to be sure that this is not entirely reducible.
Putting the 0 there.
Yes, to 0.
Sorry. Yes, you're right. Yeah, exactly. Sorry. Okay? And this is a system that satisfies the Untitled theorem. So now I know that R of Z, Rn, looks like this. Some constant time rho R minus n and n over n to the power 1/3 over 2. Okay, so when I'm looking at the proportion of Rn over an, see this is the size of my circle here. No.
Oh,
There.
Yeah. This is the proportion. This is this proportion. This over this, right? Sorry. It's equivalent. So here I have a constant C1 rho R minus n, and on the bottom I told you that it also satisfies the Untitled theorem, and we did the computation. So RA minus n. So if I want to say that, so this is C1, this is C2, this is a constant, I just need to say that rho R is equal to rho A, okay? And basically rho R is the radius of convergence of the series of R, and rho A is the radius of convergence of a series of arithmetic expressions. So this, I can prove it, usually in the general case we prove it inside the Untitled framework, but here we can prove that they are the same just easily. So the idea is that the set of completely reducible trees, they are included in the set of arithmetical trees. So Rn is less than An. So this implies that rho Ra is bigger, no sorry, in the opposite direction, is less, the radius of convergence of A is less than the radius of convergence of R. Yeah. And for the other direction, we can see that if I'm looking at all these trees, a times, a 0 on the left, and any arithmetical expression on the right, this is a class of trees, so this represents a class of trees, that is included in my completely reducible trees. Okay? And if I'm looking at the generating series of this class of trees, it's Z square A, it's the generating series is Z square A of Z here. And so this means that the radius of convergence of this class of trees is bigger than the radius of convergence of R here. But the Z square doesn't change anything for the radius of convergence, so it's the same as the radius of convergence of A. Okay, so rho A is bigger than rho R. Okay. So this cancels, and this tends to cancel. Okay. So I think I don't have much time, but okay, this shows you this picture, and so I can lied a little in my construction, because when you want to generalize it with arbitrary absorbing pattern, here I used a lot the fact of, even if I forgot about it, but the fact that the absorbing pattern is a leaf, so it's very easy to remove it. In general case, it's a tree, So to be able to remove it without using some minus that are not compatible with the arbitrarily good theorem, I have to do some what is called iterations that will build bigger systems of trees. But this kind of looks like the same. It's the same general idea, but just with more technical stuff. Okay. And to give you just one last result, because this questions the relevance of benchmarks, but maybe not the relevance of average case analysis. So we proved in fact that a stronger result is that when you are looking at a set of expressions with an absorbing pattern, that satisfies so the property that I say, so it's described by combinatorial system and it cannot prevent some absorbing phenomenon, it has an absorbing pattern. Then the expectation of the size of the reduction of a random tree uniform of size n is bounded by a constant of n. So this means that if you are generating big trees of size 1 million, 1 billion, 100 billions, the expected size of the reduction, just you apply this very easy reduction, they just compute and just recognize the absorbing pattern and simplify it. In average, you obtain something that is bounded by a constant independently of n. So this is completely degenerated. The main intuition behind that is that a random tree is not well balanced. So you have a big branch here of size square root of n and smaller trees here. And the idea is that whenever you have here a times and a 0, for instance, it will cut a huge branch of your random tree. So this is why it's not specific to the expression I'm looking at, but more at the uniform random distribution. Okay. And actually, we showed a stronger result than if you are looking at the moments of superior order. They are also bounded by a constant. And so this implies that if you have an algorithm that is dealing with expressions that has a worst case complexity polynomial, I can derive a new algorithm that will do the same thing, but that will have an average complexity constant, bounded by a constant. And the idea is just I have A and I just build sigmas and I compute A. This is my new algorithm. Okay. So, but I mean, it just says that the theoretical study of algorithms that are looking at, that are have as an input some expressions following the uniform distributions, they are not really relevant, but because they are focusing on the behavior of the algorithm, whereas the distributions of the expressions they are looking at is completely degenerated. Okay. And I think I will stop there.
Any questions? Have you thought about a better way of generating the expression?
Well, we really don't know, really. We studied the other distributions, the BST one, and we didn't have the same result. But the problem is more like we just had some really simple semantic rule, and so we found that in this case we were not able to reduce as much as in the uniform one. But that doesn't mean that it's not degenerated. That just means that the absorbing pattern is not sufficient to completely degenerate it. And in some special cases, the exact semantic has been studied for the BST-like. It's in the PhD thesis of Cecil Meyer. And they studied Boolean expression under the BST distribution, and they showed that it was completely degenerated. So my guess is that for the BST distribution, you have to look more at the semantics. You cannot have some general results that will apply for everything.
So by BST you mean like with this combinatorial rule as a converse from
Yeah, so BST is, I think it's the most natural algorithm that you would think about when you would like to generate some random trees. So the BST-like distribution, so it's just you want to generate a tree of size n. You give a probability to your operators. And so I want to generate a tree of size n. So what I do is just I pick a random operator, times for instance. Okay, this is binary, so what will I say? I will pick randomly the size of my left child between 1 and n minus 2, and then I will generate recursively the left child and the third child. And this is not the uniform distribution, this is what I call the BST-like distribution.
Right, it's pretty complicated. If you don't do the tree size uniformly, it could be a pretty complicated family of distributions.
Yeah, totally. Yeah. So most of the time benchmark, they use the BST-like distribution. But what was kind of intriguing is when you look at the code, what they are using, they really don't care about the semantics. It's completely a syntactic question. And they give up to the user to define some probability operations, probability distributions that will kind of look like what it's used in real life. And so the uniform is mostly used for average complexity because it's easier to analyze.
Any other questions? Could it be true that in the uniform distribution setting that these absorbing patterns are really the only thing forcing some object having a constant proportion? So
I wouldn't say so. I think just one easy way to have a general framework that will work for a lot of things. One thing is that we showed that it tends to a constant here. Okay, this is bounded by a constant, but when it's unidimensional, it's bounded by a constant. It tends to a constant. Sorry. So we showed that when it's just one-dimensional system, we showed that it's not only bounded by a constant, but it tends to a constant.
What is a one-dimensional system?
It's something like when it's not a system, just one line. Yes, okay. And we wanted to do the experiment and to show that it was tending to a constant. So we draw some random trees for regular expressions, but it's kind of the same. We went to something like 30,000 as the size of the input, and we computed sigma of t, and we expected this, right? Nice convergence. Was to be able to give numerical things in the paper. But instead of this, we got this. So we were, oh, what is going on? So we tried a little bit longer. We changed the way of generating trees to be able to go way more than 30,000, and we obtained this. So okay, this was not linear, but it was still not converging to a constant. So for regular languages, we computed the constant. In fact, the constant was 3 million something. So why this constant is so big? It's just because our absorbing pattern is really, really small. We only look at A plus B star. And if it's B plus A star, it's not anymore an absorbing pattern for us. So it's a really, really small semantic rule. So this implies, because it's applied to a lot of different expressions, that the constant will be bigger. But for regular expressions, we kind of use more semantic rules, just not to have some absorbing pattern than other phenomena that will reduce the size of the tree. And we obtain that in average, when you add more rules, semantic rules, for specific to regular languages, the constant was 77. So this was a lot more. And the proportion here for 2 letters, so the proportion here, it was between 30% and 45%. So it was a huge amount of expressions that represented the set of everywhere.
So even the 77 is an upper bound on what the real minimal semantic size of
Yes, it's just an upper bound because we did it by having some heuristic way of detecting that some expression trees, some regular expressions, were what is called universals, like represent the set of all words. But doing it automatically is not possible because it's a problem that is p-space complete, so it's harder than NP. So we miss a lot of expressions, but it's sufficient still to reduce the constant from 3 million to 77. So I think in this case we can say that really it's not something we want to have.
Okay, so let's thank Florent again.